introduce Gwyneth, who is the current chair of the Women in Maths Committee of the LMS and has been on the committee for 6 years, 7 years perhaps, and has done a tremendous amount of work for the committee and for the mathematics community and for women in mathematics in particular. She's also a very good mathematician who has had many honors and awards, and she'll tell you a bit more about it. So let me not delay calling Gwyneth up to give our first talk. Thank you.
I'd like to thank both John and Beatrice for their welcome. I feel a bit bad standing up here giving a talk, and I'm chair of the Women in Maths Committee, which is organising this event. We sort of discussed who the speakers could be at a meeting, and people said, "Oh, you should talk." I said, "I can't talk, I'm organising it." And Beatrice very kindly said, "No, I'll organise it, you talk." So here I am. So I'd really like to thank Beatrice, who's done a fantastic job in getting a really good programme together, and it's really lovely to be here to see so many of you. We were hoping to maybe get 80, and I think we've got around 100, which is brilliant. So it's been a really fantastic year for Women in Maths. So we've had a launch at the House of Commons. I've been on Women's Out this week, and it's just kind of suddenly everyone seems to be interested. I've had departments queuing up saying, how can we get more women in the department, and how can we help their careers to flourish? So suddenly I think from being on a committee that we've been trying to do things for years, and no one's really been paying that much attention, it feels like suddenly the outside world has woken up and wants to know what they can do. So I think it's quite an exciting time to be a woman mathematician, and you have a much better chance now of succeeding, so I wish you all the very best, and it's really lovely to see you here today. And thank you also to the Isaac Newton Institute, who as soon as we contacted them and said, could we possibly have another event here, they said, yes, we'd love to have you. So, and everyone's been really good at getting things together and making things work, so it's really, really good to be here. So I should tell you a bit about my maths, and also I wanted to just tell you a bit about how I got to where I am today, and just my life in general. So this is a bit of, really this is my life. So, starting when I was an undergraduate, actually I was an undergraduate here, so it's very appropriate to be talking about my mathematical career back in Cambridge. I was an undergraduate at King's College in Cambridge, so there it looks very idyllic. Of course it wasn't always like that, but it was a very nice place to be. So this is a kind of intersperse of how my life and also my maths. So in Cambridge I met my husband, who was also a mathematician in the year above me, and mathematically I particularly enjoyed analysis, and especially complex analysis. And because I particularly enjoy complex analysis, I talked to my director of studies at the end, my sort of third year, and said I'd really like to do a PhD and I'd really like to do complex analysis. And he said, well, in that case I think you should go to Imperial and see if you can do a PhD there, because they're very good at complex analysis. So I went to Imperial. So this is slight contrast. I was just looking for pictures on the web, and I thought, well, actually, it did look like that quite a lot of time. This grey building in the rain. So it was a bit of a contrast to Cambridge. And I was sort of stuck in an office. Well, there were two of us who used to go in every day, and I didn't think I was very good, because I would go in whenever I got there, he would be there, and whenever I left, he would still be there. And I thought, wow, what was he doing? And then 2 years in, he was offered a lectureship and turned it down. And then I thought, he's not typical, is he? I should stop comparing myself to him. So he was Trevor Woolley, he's now an FRS. So that was. So probably one lesson of that is don't underestimate your ability, because I had no idea if I was any good, and I was comparing myself with this future FRS and thinking that was normal. So mathematically I was, I'll talk about the maths in a minute, but I was studying iterating functions on the complex plane. So Julia sets, the Mandelbrot set, they sort of, so this was a horrifyingly long time ago, this was 1988, so my supervisor was Noel Baker, and he'd been proving results on this quietly for a long, long time. He was a very modest man, but he was very, very talented and proved lots of really nice results, but nobody had really taken any notice until the sort of 80s, when computers came and people started producing pictures of things like the Mandelbrot set, and suddenly everybody got excited. And I'm actually just a pencil and paper person, and we just sat quietly in Imperial proving things on with paper and pencil, but and actually I didn't go there because I wanted to do iteration. I went there because I wanted to do complex analysis, and it just happened that that's what he was doing, and I didn't really know that this was a new exciting area, and we sort of sat there quietly proving things. But it was so mathematically I really, really enjoyed it, but it was kind of sitting in an office on my own, kind of, as I'm sure many of you know. But that satisfaction when you get those results out, was nothing quite like that. So in 1990 I got married. So this is relevant because I finished my PhD in 1991. So at that point, I wanted to carry on, and what I would really recommend to any of you at this stage is kind of talk to people much earlier than I did. If you want to go on to do a postdoc or something, then you really need to be starting to talk to people and just ask what the options are, finding out where you might be able to go, because it might require people to apply for funding so that you can get a position somewhere else, and that can take a year to kind of start talking to someone. They could apply for a grant before you could go. I think in my own career I seem to have wandered along, and it's kind of actually happened all right in the end. But the more you can do to try and take charge of your own career is better, really. So at this point I was married and we were living in Farnborough, and so I applied for something at Imperial and didn't get it, and I think I sort of sat there thinking, well, no, I haven't done any teaching, no, I realised that could be a problem, and probably, again, underestimated how good I was, and in the end I just wrote to any university I could commute to and said, do you have anything? I'm looking to, I'm a mathematician, and there's anything I can do. And luckily for me, Southampton wrote back and said, actually, we've got some engineers who need maths teaching, would you like to come and teach some engineers maths? So the next 3 years I actually was at Southampton. So this was also a grey building, a very tall, much taller grey building. It was kind of, if you know this maths tower at Southampton, it's kind of, I think I was on floor 7, I can't quite remember that. But it was a very, very friendly department actually, and they kind of saved my life. If it hadn't been for them, I wouldn't be here today. So they kind of, when I first got there, I was literally paid by the hour to teach engineers, and the next year they gave me a half-time lectureship, and the next year they gave me a full-time 1-year lectureship. And there wasn't anyone there in my area, but I was just there. They were kind of keeping me going, and I would go back to Imperial for seminars just to keep some link in with my supervisor. And I sat quietly in my office and I carried on doing what I'd been doing at the end of my PhD, and I wrote lots of papers on dimensions of Julia sets, which got increasingly complicated, I think. So those were the tough years in my career history, but I'm really glad that I stuck at it and carried on, and then things got better. So after that, I did finally get onto the ladder, having applied for several jobs and not got them, and then a 1-year research fellowship came up at the Open University. This was in 1994, and then at the Open University there was somebody else in my area who's very good, so this was a really, really good place for me to go, and I had this 1-year research fellowship, and I could just do research, which was great. Apart from after my first 3 months there, I remember trying to prove these results and sitting there, and at the end of the 3 months I had that much rough paper and no new results. And then I took 2 weeks off for Christmas and came back, and it all just came out. So again, I think hanging on is a key kind of message, probably, sticking at it in all kinds of different ways, kind of. And then I was very lucky. A lectureship came up at the end of the year, which I got, and then I was on and could breathe a huge sigh of relief and know that I could just concentrate on things and not have to worry about having a job. And I carried on writing papers on dimensions of Julia. I was very narrow, but by this time I probably was the world expert on them. Dimensions of Julia sets. So I'll talk a bit more about this in a minute. But again and again, the other person who was there was trying to kind of let me get my own career going, and so we didn't really talk much at that point, kind of, but we do now a lot. But at this point, I was sitting there in my office writing papers, and then personally, so I then had 2 children. So Tim was born. He should have been born in 1997. He was 9 weeks early, £2.6. So, and Abigail was a huge weight of £3. So I had very exciting pregnancies involving lots of exciting times, and that was quite stressful. But they're now fantastic children, doing very well. In terms of my research, this again was the next point of kind of, well, everything changed. I'd gone from sitting in my office with all this time in the world to kind of write papers, and suddenly I had 2 children. I took 9 months maternity leave with each child, and I switched to working half-time. So the OU was fantastic about that. They were very flexible, and I was able to work half-time. Obviously, my research career well, the research time got cut dramatically. So I'll come back and talk about that in a minute, kind of. I should talk some maths at this point. So I'll talk about some maths. What is this dimensions of Julia stuff I was doing, and then talk about sort of post-children and what happened to my career after that, which is really the next stage. So maths. So what I do is complex dynamics. So we're taking a function of the complex plane to itself, an analytic function. So it could be a polynomial or an exponential function. Lots of different functions you can take. And we're looking at the iterative f. And so this series really started by Fatty and Julia right back at the beginning of the last century, but it kind of really sort of got interesting, or lots of people got interested around the 1980s. So, the first set was defined, which is that I've been looking at, especially for the last 10 years or so, is the escaping set. So this is very simply defined. It's just literally you take a point and you apply your function again and again and again, and you look at that point if it goes off to infinity as you keep on repeatedly applying your function. So the escaping set has a very simple definition, and it's really come to play a very significant role in complex dynamics over the last 10 years or so. And you can actually define the other fundamental sets in complex dynamics in terms of this escaping set. So the Julia set, which you may have heard of, not often defined this way, but you can define it to be the boundary of the escaping set. So the Julia set is the chaotic set. If you take a point in the Julia set and you iterate it, it can do lots of different things. The important thing is that points nearby have very different orbits when you keep on applying your function. So the Julia set is a sort of unstable set that you can have points nearby with certain types of behaviour, and then the point itself has a different type of behaviour. And then the last set, which I was trying to get away without defining, but got to the end of the talk and realised that I need to define it. So the Fatty set is just the complement to the Julia set. So this is the set of points which is stable under iteration. If you take a point and you follow its orbit, then any points nearby are going to follow the same kind of orbit. They have the same type of behaviour. So this is an open set, the Julia set, closed set. And the escaping set isn't open or closed. It's quite complicated topologically. So if you want to look at, think about these sets, the simplest example to think about is just taking z squared. I'd rather use the board. It's probably not going to be on the screen, but I can't survive a whole talk without the board. So if you look at z squared, and this is the unit circle, then all the points, if you take a point bigger than modulus 1 and you square it, it's just going to get bigger and bigger and bigger and bigger, and all the points out here, when you iterate them, they just go off to infinity. You take a point inside the unit circle, so I should put f of z as z squared. If you take a point inside the unit circle and you square it, then it's going to get smaller and smaller and smaller, and it's going to get sucked into this attracting fixed point 0. So for this function, the Fatty set has two components, this one outside the unit circle and this one inside the unit circle. The Julia set is just the unit circle, so that's fairly boring, though it's not an exciting, pretty fractal set like most Julia sets are, but it illustrates what's going on. So this is the Julia set, and the escaping set is literally just all these points the outside of the unit circle. So that's, and you can see the Julia set's the boundary of that. So the escaping set is all these points out here, and the Julia set's the unit circle. And I say what I did for 10 years was look at dimensions of Julia sets. So how can you describe the size of the Julia set? So this is a very simple example. It looks like a nice one-dimensional set, but as soon as you look at more interesting functions, so if you look at f of z is z squared plus c, just take a small value, say 0.1 or something, then you can get a very similar type of behaviour here, but you'll find that the Julia set is it's still just a Jordan curve, but it's a Jordan curve of infinite length. So clearly things have got more interesting, and you can then start to look at the possible dimensions of the Julia set, Hausdorff dimension, box dimension, just different ways. How can you describe the size of this set? So that's on the next. So this is the Mandelbrot set. So naught is kind of in the middle of this big cardioid here. And if you look at any value for c in the main cardioid here, then you'll find that the Julia set is just a Jordan curve like I've drawn there. And roughly speaking, as you go away from 0 towards the edge of that main cardioid, the Julia set gets more and more wiggly, and you can get the dimension changing from 1 in the case on f z squared, and you can actually get the dimension going all the way up to 2 as you go out towards the boundary. So there's a big paper by Shakira which shows that you can get that. And then if you if you're outside of the Mandelbrot set, if you take a value of C outside there, and you look at the Julia set there, the Julia set for values of C outside the Mandelbrot set is totally disconnected. If you look at it on the sort of negative real axis at -2, the Julia set is just the interval -2 to 2. So it's one of these very simple examples where the Julia set's just a line. And if you go for C less than -2, then you get the Julia set's a Cantor set in the real line. And as you take your values of C being more and more negative, you find that this Cantor set gets more and more spread out and the dimension tends to 0. So just by looking at this very simple family of functions, this is the simplest family of functions you can look at, really. So there's a result by Garber from 78 which says that the dimension of the Julia set is always strictly positive, whatever value of C you take. And in fact, any polynomial or rational function, or in fact entire function, you still get the dimension is always strictly positive. But just by restricting yourself to looking at this very simple value of functions, you can get the dimension takes every value between 0 and 2, apart from 2. That was kind of known for polynomials. What I was looking at as my supervisor was transcendental functions, so exponential functions, things like this. So at that point when I came into iteration in the 80s, most people were looking at z squared plus c, or kind of polynomials, or that was where the real kind of interest was. There were very, very few people looking at transcendental functions, so which was nice because it meant there were those big questions and very few people looking at it. So. Oops, I forgot to tell you about these. Okay, so these are some pretty pictures of Julia sets for quadratics. So that's just showing. So this is the this is the boundary of this black thing here is the Julia set. So you can just see that as you increase your value of C, it's getting more and more wiggly and getting the dimension going up. That's a totally disconnected one outside the Mandelbrot set. These are produced by my collaborator. I don't know how to use computers very well. And that's one on the negative, that's the value of C on the negative real axis, and you get the Julia set, the Cantor set. Okay, so exponential functions. So this is, it's the kind of classic family of polynomials you look at is z squared plus c, then the classic family for transcendental entire functions is exponential functions. So there's now lots and lots of work being done on exponential functions. This is a typical one. This shows you the Julia set for quarter e to the z, and it looks very different to the Julia set which we're just seeing for these polynomials. So here you've got the escaping set is very similar to the Julia set. The escaping set is just what's called a Cantor bouquet of curves. So all these sort of yellow bits going down the middle here are in the escaping set. So you've got the real line from some points on is in the escaping set, and you've got all the sort of translates of that by 2 pi I going to be in the escaping set. You've got all the pre-images of that are in the escaping set. So you get this whole sort of family of curves accumulating everywhere. And if you take a cross section through that, you'll get a Cantor set. So you've got curves accumulating everywhere, forming your escaping set. So very, very different to the escaping set for these polynomials, where the escaping set was just a big open neighbourhood of infinity. So for any polynomial, the escaping set is just a neighbourhood of infinity. When you look at transcendental functions, it's much more interesting, and here is a Cantor bouquet of curves, and actually it's all in the Julia set. And the Julia set is just the escaping set plus all the endpoints of those curves. And actually all the interesting dynamics is happening on the endpoints of the curve. So all the curves escape to infinity. Everything in the blue bit just iterates into an attracting fixed point, and the endpoints are doing all kinds of interesting things. Some of them are periodic, some of them are fixed, some of them are going to infinity really slowly, whereas all the rest of the curves are going to infinity really quickly, and some of them are just wandering randomly around. So the endpoints are an interesting bit. In terms of dimensions, when I started my PhD, there was a paper by McMullen had just come out, a big paper, the first paper on dimensions of Julia sets for transcendental functions, and he's showing that for these exponential functions, the Julia set and the escaping set have dimension 2. That was the first one was known, nothing else was known. And then following on from that, well, lots has been done, but the most striking result that's been done since then is by a Polish girl, the Guzikowicz. This was actually her PhD thesis, which is one of the most striking PhD theses I ever seen, I think, but she proved that if you look at the curves without the endpoints, they have dimension 1, if you look at the endpoints for curves, they have mentioned 2, which I still can't get my head around. That's one of those. That's one thing that's really nice about this subject, is that it just has these paradoxically sounding results that you think couldn't possibly be true, that are true. So somehow the endpoints are bigger than the curves that they're attached to. So that's exponential functions. But that was all that was known. So this is what when I said I was sitting in my office proving results about dimensions of Julia sets. I was looking at what are the possible values of dimensions of Julia sets for just any transcendental entire functions. And Mullen has shown that you could get dimension 2. So my supervisor said, well, I think there's things you could look at here. And I said, this paper looks really complicated. I'm going to do something else. So I did something else, and then he got me back, and I said, okay, I'll do this. And then for 10 years I did nothing else. But I was very lucky in the sense that there was this big question. Nobody else was looking at it. And so there were lots of things you could prove. So obviously, I've summarised 10 years in 2 bullet points here, but so there was other stuff as well. Kind of, these are the highlights of it. But for a transcendental entire function, the Julia set always contains continua. So the dimension is always at least 1. And what I showed was that actually the dimension can take any value between 1 and 2 apart from 1. So that was several years' work. And the other result, which is a very complicated paper I wrote in Southampton, which has since been proved much more simply and beautifully, is that if you, in the special class B, which lots of people look at them and dimension the Julia set is strictly greater than 1, and then the open question has been ever since there, could you get dimension equal to 1? And I would have guessed that you couldn't, because the Julia set is always incredibly complicated, but Chris Bishop, who doesn't work in complex dynamics, is a complex analyst, came in last year and suddenly solved lots of open conjectures in complex dynamics by bringing in lots of complex analysis stuff and constructs an example where the dimension of Julia set is equal to 1. So you can actually get every value between 1 and 2. So that's what I did for 10 years, and I'll try and do the next 10 years in my life. So going back to me as a person. So I think when I last finished at the beginning of the talk, I got up to having children, and so I come back and say what happened after I had children. So I did all this dimension stuff, and then I had children. So that was Tim. Okay, so in 2000 I won the Whitehead Prize, which was extremely good timing from my point of view, because at that point I was working 0.5 with a tiny baby and struggling to get any research time. And I think for the first, well, actually, when I got the email saying I got this prize, my first reaction was, how do I tell them they've got the wrong person? Luckily, I didn't reply saying, I'm sorry, I think you made a mistake. But I probably, eventually sunk in that maybe my research was okay after all. And I was stopping and thinking, well, this is ridiculous. I just won a prize and I'm struggling to get any research done. I have to do something about this. And so I did go through my teaching at that point and just try and work out what could be cut, kind of an undergo. And actually in the next maternity leave, thinking carefully, well, how am I going to sort this out? This is I have to sort of try and get some research time back and get this to work. So again, for those of you who are at this stage, it is really hard at this stage, but do hang on in there, because it does get a lot easier as the children get bigger. And there are lots of ways of helping. So 2002, so when I went back from having had to go, I was promoted to senior lecturer, and also I began to collaborate with Phil Rippon, who's my colleague at the Open University, and that was it. We've done a couple of papers together before, but we sort of then started on a sort of big project where we suddenly had lots of ideas, and this was fantastic because it meant we could talk at work, we could just bounce ideas off each other. He had more time than me at that point, so he could do lots of the writing up. I wasn't going to conferences once the children were little, but he was still going to conferences. He could talk about the work, sort of keep me networked into the community, come back, tell me ideas. And one of the biggest ideas we had, he went to a conference which I couldn't go to. He came back and said, no, I had this idea, but I really can't see how to make it work. And I said, well, I think you can make it work like this. And then we wrote a paper, and that was fantastic, having somebody else to talk to. And that really helped me get my research going again. And we've kind of carried on writing papers ever since, and it just works very well the way we work together. But I would really say, talk to as many people as you can, keep networked in. And the other thing, actually, in retrospect, looking back, that would have been really useful at this point would have been to have a research fellowship, kind of, and it crossed my mind that you could apply for a research fellowship, but there are research fellowships out there, and if I could have just concentrated on research and not been doing teaching in the 0.5 that I had, that would have made my life, that would have really made life a whole lot easier at this point, because that was a difficult point, just to keep going, kind of. So that's something else I would just say, and think about it before you go on maternity leave, because writing a grant application takes months, I now know, kind of. But so talk to people before you go. Think about how you can make it work when you get back. Kind of, I sort of struggled through blindly, kind of sleepily, kind of not quite knowing what I was doing, kind of, and came out the other side. But the more you can do to kind of control your own career and where you're going, the better, really. But, so that was 2002, 2003. I went up to 0.6 and I started going to conferences again, and life was beginning to get a bit easier. So 2005, 2007, I worked up kind of. Actually, this was fantastic. Going down from 1 to 0.5 was really hard, and it took a while to actually get my workload halved, I think, kind of. And in reality, it doesn't halve, and you still get the emails. And going up by 0.1 is brilliant. Nobody notices you going up by 0.1. You get the extra money and you get the extra time because you've paid for more childcare, and I felt like I was gradually getting back my research time each time, kind of. So the going up was delightful. And in 2009, I was promoted to a professor, and I would say I'm extremely grateful to my colleagues all the way through this, kind of. So actually, I found in retrospect I was nominated for the prize by colleagues, and that really helped my career. The promotion cases were really written for me by the colleagues. They were telling me, "You are good, and you should go for professor. We will write your promotion case for you." So I'm incredibly lucky to have been in a very supportive department, letting me work flexibly and also supporting my career. And 2012, last year, I finally came full time. So Abigail went to secondary school last year, and this is partly because they were now at secondary school, and also partly because about a year ago the children found out I was part time, and they said, "What do you mean you're part time? When is the part time bit?" Okay, right. Maybe I should get paid for working full time. But it has been incredibly useful, allowed me to kind of just be there when I got home from school, and so the OU has been a really flexible place to work, which I'm very grateful for. So I probably now have about 5 minutes or maybe 10 to get through the rest of my what Phil and I have been talking about for the last 10 years in terms of this escaping set. So I'll try and summarise this very quickly. So what is the escaping set? So interesting, what have we been doing? Well, lots of work on the escaping set is motivated by a mathematician called Eremenko, who made 2 conjectures in a paper in 1989. So he conjectured if you have a transcendental entire function, then his main conjecture was that all the components of the escaping set are unbounded. So if you think back to this picture we had of the exponential function, if I can get that right. There we go. So for the exponential function, the escaping set is basically made up of all these curves going off to infinity. So really he was kind of wondering whether this was true more generally. So firstly, is the escaping set made up of all the components unbounded, and can you actually strengthen that and say actually all the components are curves? And what we had proved was that for the closure of the escaping set, all the components are unbounded. The question was, what happens if you innocently take that closure off? Well, it makes a huge difference. So it's a very simple question to state, but it's very hard, and there's lots of people been working on it, and we now know exactly how hard it is and how complicated the escaping set is. But it's a very nice question, and that has motivated lots of research. So there's various results on this. So there's the sort of biggest paper probably paper by Russian professor Ramsden Schleicher, who showed that if you're in a certain big family of functions that is studied by lots of people, then this is true. You get the escaping set, it is made up of all these curves. So this family includes the exponential functions and lots of other obvious functions that you might think of in this family. But the paper also shows that the strong version of the conjecture is false, so that if you look at path-connected components of the escaping set, even in this class B, this nice class B, you can get a function where all the path-connected components are actually points, so they're as far from being curves as they could possibly be, even though if you just look at components in terms of disconnected components, they're all unbounded. So it's one of these really strange functions to get your head around. The components are all unbounded, but if you put the stronger definition path-connected, then the components are points. So that, again, helps to show how complicated this escaping set is and how hard the questions are. So what Phil and I have been doing, what we've done is managed to make quite a lot of progress by restricting ourselves to looking at something called the fast escaping set. So if I describe what the fast escaping set is, if you take a circle of radius r, and then you can look at so m of r is find the maximum value of your function on this circle radius r. So if you look at the image of this circle under your function f, so maybe it looks something like this, and then you take the maximum value on this image and draw a circle through there. So that's a circle of radius m of r, and then you could do the same thing again. You could look at the maximum value of your function on this bigger circle, and then that would give you a new circle, which we'll call circle radius m2 of r, and so on. So you keep on taking the maximum modulus of your function on each of these circles. And what we're interested in is points that escape to infinity, but at this sort of maximum rate at each time. So they're really going to infinity as fast as possible. So if you take a function, a point outside here, it maps outside here, and maps outside here, and so on. So it's really going off to infinity really quickly. So I've put the definition of that on there. But, don't worry about the definition exactly, but the important thing is that it's going off really, really quickly. And it turns out that when you look at this fast escaping set, you can start proving things. So actually in Eremenko's original paper, when you go back and look at his original paper, it actually follows from his results that you still have this really nice link that if you just restrict yourself to this fast escaping set, you still get the Juliet set. It's the boundary of it. So it is a nice, interesting set worth looking at. And one of the nice things about it is it's made up of an increasing union of closed sets that has lots of nice properties that the escaping set doesn't have. And the sort of big result which we've proved is that if you restrict yourself to this fast escaping set, then all the components of that set are unbounded. So even Eremenko's conjecture was that all the components of the escaping set should be unbounded, which we still don't know at all. But we can say that if we look at this fast escaping set, then that result does hold for that. So the components of the fast escaping set are unbounded. So this is what we proved from when I had little children and Phil went to a conference and came back, and then we sort of put our ideas together and the result came out. And then things have just gone on from there, really. One of the consequences of that is because we know the fast escaping set is always non-empty, we can show that the escaping set always has at least one unbounded component, which is obviously a long way from showing that all the components of the escaping set are unbounded, but it is the strongest result that we know in general. So that's something that's nice about it. So
transcendental or any of them?
This is for transcendental functions. So I'm going to have to zip through some of these things here. So the next thing which we proved around the same time, that if you look at a certain class of functions when they have, so this Fatu, if you remember the Fatu set was all the points where the iterative behaviour was stable. If you have a function with a component of that stable set that's multiply connected, so it's got a hole in it, then you can prove something. So if it has a multiply connected Fatu component, then it's basically it's a ring like this, and you can show that it's a ring that maps out to a bigger ring, and then that maps out to a bigger ring, and so on. And any multiply connected Fatu component eventually maps into a structure that looks a bit like that. Then one thing which we showed was that each of these rings is in the fast escaping set. And if you remember, what we'd also just showed was that all the components of the fast escaping set are unbounded. So this belongs to an unbounded component of the fast escaping set, and so on. And then actually, if you think about it, what that means is that the fast escaping set must actually be connected, because if you take any component of the fast escaping set, it's unbounded. If you had another component, that would also be unbounded, and so it would be joined together by one of these rings. So you only actually have one component. So what we actually have is that the fast escaping set is connected, and actually once you've got that, you can then join on all the rest of the escaping set, so that's connected, and it has a structure which we call the spider's web, because you have all these sort of loops going around, and it's joined by all these sort of spokes going out. And this was nice because actually, so that means that these functions, you've got Eremenko's conjecture is true, because in a very strong way the escaping set is connected. So certainly all the components are unbounded, it's just one big unbounded component. And it also means that the escaping set now has a very different type of structure to what had previously been looked at. So the example I had earlier with these exponential functions, with these sort of cantle decays of curves going off everywhere, was what everyone typically thought of how the escaping set looked for a transcendental entire function. And then suddenly we seem to have proved that for these functions, the escaping set was this construction that had all these loops in it joined by rays going out. So it's a very different picture. So that was, we did sort of stand at the wall going, no, this can't be right, because I think people thought if you had a counterexample to Manco's conjecture, it would probably come from functions like this, because you'd have these rings in the escaping set, and then maybe you could disconnect it between the rings. But suddenly we seem to have proved that actually everything was connected, which was the strongest you could possibly hope for. So that was definitely standing at the wall going, no, let's check this, it can't be right. But that was nice. And then, okay, so this is just the definition of a spider's web. So we call this structure a spider's web. It just means it's got loops in its connected set. And then here's a picture. So we called this informally a spider's web, which was, it was a sort of new structure which we were pleased to have found. And then we realised using results in complex analysis you could prove lots of existence theorems that this structure did exist for lots of functions, but it was actually quite hard to find explicit examples of functions which had this structure. But one example is cos z plus cosh z plus. This is one of our PhD students, luckily was better with computers than we were, and produced this pictures for us, which we're very pleased by because it actually does look like a spider's web a bit. So all this structure in the middle, you can see these sort of loops. Obviously, it's an approximation to it, but all the yellow bits are sort of approximation to the fast escaping set. There's all these loops everywhere, and it's got lots of rays getting out, and this structure should be the same here, but the computer can't deal with the arithmetic out here. But you've got this very intricate structure, which sort of looks different to the cantle decay structure. And I think I should just skip over the next and just go straight to the end at this point. Basically, once you've got this structure, there's lots of questions you can ask about it, and you can start suddenly you've got a whole new kind of possible way the escaping set looks, and you can start to prove lots of results about it. So we've been doing that. So there are lots of possibilities here which I will skip through. But the important thing is that if you have this fast escaping set has this spider's web structure, then so does the escaping set. Manco's conjecture is satisfied. Also, you can show that there are no unbounded Fatu components, which links to another conjecture by my supervisor, actually Noel Baker. So he had this conjecture, again I don't want to go into details, but it was that if you have a big class of functions, then your function has no unbounded Fatu components, and you can prove this with the spider's web structure because you can show that the loops you can force to be in the Julia set, and so all the Fatu components have to lie between these loops, so they're definitely bounded. And when we looked at all the proofs of Baker's, all the partial results on Baker's conjecture, you could see that actually the proofs actually told you more than that there were no unbounded Fatu components for these functions. They were telling you that actually the fast escaping set had this spider's web structure. And so actually we were able to show that for those functions, Manco's conjecture was satisfied as well. So somehow there was suddenly this link between these two conjectures which looked very different to each other originally. At that point, we managed to have quite a bit of research time, but we were kind of, suddenly things looked quite interesting and we wanted more research time. So we kind of applied to EPSRC for funding to fund ourselves for 3 years, which people told us you couldn't do, but I phoned up EPSRC and they said, no, that's fine, we don't know why more people don't do it. So again, do kind of think about doing it. There were just 2 of us, we just applied for funding for half of our time for each of us for 3 years, and they luckily thought this was a good thing to do, so they funded us for 3 years. That finished last year, and now in my horrible teaching year. And we've just managed to get more funding for another 2 years to investigate this link, kind of really by saying, actually, this doesn't seem to work quite the way we thought it did when we put the first grant in. Can we have some more money to try and see what happens next? So that's where I am now, and I shall stop at that time.
So we're a bit beyond the time, so if anybody has 1 or 2 questions. Yes, we can.
I'll be around.
So you mentioned with your funding that it's all been for you. Have you ever considered postdocs and students and things?
Yeah, so we've had this is 2 separate grants. This means for myself and Phil, and we've also just got a postdoc who started on the grant that we a separate grant that we put in for, again, about a year ago, which was actually designed around something. We had somebody in Germany who wanted to come and work with us, and we put a bid in for him, but then he couldn't come, so we've got somebody else working on it.
Do you think that's a useful thing to do when you have young children? To have a postdoc doing the work for you while you're
I don't know, in my experience it takes work to supervise the postdoc. I mean, it depends how you are. And I would value the time for myself more at that point than, because I think at that point maybe they use it like they might find a postdoc and I went, but actually I need time for myself, kind of, rather than necessarily to be trying to think of ideas for somebody else to be doing something. I mean, it partly can depend how it works, kind of, but I would really value the time with young children for research myself, kind of, and there are research fellowships you can apply for, and that's what I personally would have found most useful at that point. But
Can I say that we'll have a lot of discussion on general issues?
Yeah.
Maybe now, if anybody has a maths question, we can, either a coffee, lunch, or at the discussion groups, all these issues about funding, family, and so on. We have a lot of time for it. So perhaps let them. Does anybody have a maths question about?
I was just wondering what applications this has.
in real life.
There might be.
There might be, yes. Yeah. Yeah, so I am very much a pure mathematician, and I mean, one thing that, the iteration is kind of used for sort of Newton's method, so there are people in this area that kind of, and one paper I've done has been vaguely related to this, so that there are links with kind of Newton's method, and that's certainly a practical thing, kind of.
It's also image processing, isn't it? Algorithms.
Yes.
Yeah.
Yeah.
Solutions and certain
Yeah.
things.
Yeah. No, so there certainly are kind of links with practical things, but it's not.
Yeah, I just wondered if you knew of any specific.
Yeah, so I'll say the strongest thing with the complex balancing is a Newton's method thing, and then as you say, all this sort of all the kind of fractal methods are kind of, you say, very much image contraction.
Is it the case that for polynomials, these issues of, say, unboundedness of the escaping set are sort of trivial? Or?
Yes, it's trivial. So for polynomials, the escaping set is just an open neighbourhood of infinity. So it's just, it's just.
And things like that as well, or components and that. Is it all much easier?
Yes. So for polynomials, again, they just have this one. The escaping set is an neighbourhood of infinity. So that's one component of the Fatu set, and the other components of the Fatu set are just bounded. So again, that's all much simpler.
Okay, well, I think we'll stop here, but as I say, we'll have a lot of time this afternoon and tomorrow to ask more questions, so I think we should...
Yeah, so I'm doing one of the discussion groups on family this afternoon, I think, and I also said I'd do one on grants tomorrow, so...
Thank you, Gwyneth, once again for...